afternoon, everyone. I am Valery Levitas, Iowa State University. I am co-chair of this symposium. Other two chairs are Dmitry Popov and Nenad Velasylevich. And actually, we have 5 sessions, and no one other symposium has more than 2. So we are in good shape, and it looks like we won over beach. And now I will give word to Dr. Tim Officer of University of Chicago to announce first speaker, and we will guess who is it.
Hi, so my name is Tim Officer. I'm from the University of Chicago, and our first speaker is Valery Levitas, and he's going to talk about something different than in the program. New rules of severe plastic deformation, space transformation, and microstructure evolution under high pressure.
Thank you very much, Tim. So let's see. Okay, title is announced, and I would like to acknowledge my collaborators and funding agencies. I will start with description of experiments obtained in unique device, rotational diamond anvil cell, and I will mix this with four-scale theory to explain results of experiments and to predict something. Focus will be also on extracting material properties from heterogeneous fields, and I will present some new rules which we found for phase transformation, plastic flow, and microstructure evolution for zirconium and silicon. And at the end, I will discuss shortly application to deep focus earthquake. Each high-pressure lab has a diamond anvil cell, 2 diamonds, compress sample within gasket or without gasket. This is typical scale, 0.5 millimeters, so this is hair in comparison with the sample. And main goal is to study effect of pressure on all possible properties, and also to search for new phases, especially which can be quenched and with unique properties. So what we are doing differently after compression, we twist one of anvil with respect to another, superposing large plastic shear, and this changes everything. This is device is called rotational diamond anvil cell, and I brought this device from my former group in Kiev, Ukraine, 2 decades ago, and this was initiation of this type of research. To some extent, it's similar to high pressure torsion, which is used to produce nano-grained, nano-structured materials. But difference is that we can reach much higher pressure, but more importantly, that everything can be studied in situ. And difference, I will show some example difference between ex situ study after pressure release and in situ, maybe in some cases large, in some cases drastic. We perform experiments in our laboratory at Iowa State University, but mostly at synchrotron radiation facilities at Advanced Proton Sources at Argonne Laboratory. And we have different types of rotational diamond anvil cell. And recently we started doing experiments in dynamic rotational diamond cell under controlled rotation speed. For our goals, we need to measure some parameters which were not measured before. That is why we developed some techniques. So we scan along the radius with step 10 micrometers, and spot X-ray and Raman spot is 10 micrometers. And we measure, for example, not only pressure, but pressure in each phase in multi-phase mixture. For example, here it's hexagonal inversitic boron nitride after phase transition, and you see differences 6 GPa or by factor of 2. Also using X-ray, we measure distribution of dislocation density, crystallite size, volume fraction of phases. For graphite-like structure, concentration of turbostratic stacking faults. With X-ray absorption, we measure Prof thickness profile under the load. This is due to deformation of diamond. And also we place ruby particles from both sides of sample and measure relative displacement. And this is very important because due to relative sliding of sample with respect to anvil, rotation of sample in this example is 5 times smaller than rotation of anvil. There are many effects of plastic strain, and I will start with results that plastic strain drastically reduce phase transformation pressure. And you see here our results. So, for example, for rhombohedral to cubic boronitride, under hydrostatic condition, it's 55 GPa, and under plastic straining, 5.6. Huge effect. Order of magnitude 50 GPa. Even more, graphite to diamond, 70 GPa, 0.7 GPa under shear. 2 orders of magnitude, or 70 GPa. And some phase transformation don't occur under hydrostatic condition at all. For example, silicon 3 does not appear under hydrostatic condition, but under shear we obtain it at 0.6 GPa. Also, olivine to spinel does not occur under hydrostatic condition and room temperature. We obtained it at around 16 GPa. And all this drastic reduction in pressure have potential technological application and some implications to geophysical problems. Also, plastic shear leads to new phases which cannot or maybe cannot be obtained under hydrostatic condition. Here is one example. We discovered high density amorphous phase of silicon carbide, and amorphization is considered as damage mechanism, for example, for silicon carbide armor. And since this phase transition is reversible, the only way to detect it is to study in situ. Also, recently we found new disordered superhot phase of boronitride. It even scratches diamond, and even cubic boronitride cannot do this. And we detected using X-ray diffraction and Raman. Main problem is that traditional thermodynamics fails to explain any of these effects. And the reason is that shear stress is limited by yield strength in shear, say 1 GPa. And this is expression for mechanical part of driving force for phase transition. And if you assume that normal transformation strain and shear are equal for simplicity, then they add, and at 50 GPa, contribution of shear stress is just 2%. Right? If we change here, we will get 20%, 30%. But there is no way to explain pressure reduction by order or 2 orders of magnitude. That is why we developed 4-scale theory. At atomistic scale, we derive expressions for phase transformation criterion for perfect crystal on the action of all 6 components of stress tensor. It seems to be impossible due to large combination of 6 components, but I will show also we are developing a phase field approach. And with this, within phase field approach, we derive analytically these expressions. So then we need to confirm or disapprove them. And under such loading, this is expression for phase transformation criterion. Key point is that it's linear in stresses. So in stress space, this is plane. We rotate this until plane is visible as line, and you see dots here are results of MD, here results of DFT, and you see very good conformation, and also we determine 2 material parameters. When we add 3 shear stresses, we obtain additional term. This is due to geometric nonlinearity, no additional constants. And again, deviation from this expression with MD and DFT is within 5%. So now we have analytical expression. This is for silicon 1 to silicon 2 phase transition, or phase transition criteria under all 6 components of stress tensor. And this is well beyond what was done in literature, mostly for 2 components, very few cases with 3 components. Now, but reality is in real defective crystal. And here there is conceptual problems. The high pressure community characterizes phase transformations mostly in terms of pressure. And this is correct for pressure-induced phase transitions that started pre-existing defects, for example, dislocations, tilt boundaries, and which represent stress concentrator. In this paper, I introduce new concept of plastic strain-induced phase transformation under high pressure. That is what we are studying. And they start at new defects permanently generated during plastic flow. So they represent defect-induced phase transformations and require completely different thermodynamic and kinetic treatment and experimental characterization. We develop a phased field approach, nanoscale phased field approach, consistent with atomistic simulation. And first for phase transition, then for dislocation, then combine. And let's consider model problem for material with phase equilibrium pressure of 10 GPa. And if you introduce one dislocation, phase transformation pressure under hydrostatic condition is 16 GPa. Now let's consider bicrystal under compression and shear. Dislocation nucleate at grain boundary, pile up against grain boundary, and produce strong stress concentrator here, proportion for all components of stress tensor and proportional to number of dislocations. And number of dislocations can be 10, 100. So here we have huge stress concentrator. And here our phase transition criterion for perfect crystal is satisfied, and nucleation occurs as a result of solution. And it occurs at pressure, average over the sample, of 1.2 GPa. And this is conceptual proof that dislocation pileup can reduce phase transformation pressure by more than order of magnitude. Then you see with increasing shear there is growth, coalescence, but here we neglected dislocations in right grain. If we allow dislocations, you see the transformed red region is significantly smaller. So actually plasticity plays dual role. It promotes phase transition by producing stress concentrator, but it also suppresses phase transition by relaxing these stresses. But we found some combinations of shear stresses and pressure for which solutions without dislocation and with dislocations are approximately the same. And we summarized our results of nanoscale study as new possible routes for defect-induced material synthesis under high pressure. We also have first atomistic simulation of nucleation and dislocation pileup with MD, with concurrent atomistic continuum approaches. All cases are consistent. I will discuss them a little bit later. Now, key problem in nanoscale approach, phase field approach, is that it resolves phase interface, which is 1 nanometer thick. That means that by definition, we cannot treat large samples. So that is why we develop completely different scale-free phase field approach. It's without gradient term, with different completely polynomials. And also dislocation pileups are introduced through solution of contact problem. It's also scale-free. And despite that, such simplifications, we were able to reproduce our main results from nanoscale approach. But here we can treat much larger samples. You see, we resolve 3 martensitic variants of silicon, and this is evolution of dislocation structure and high pressure phase, and this is variant 1 and variant 2. And we are able to treat large polycrystalline samples. Here it's more than 900 grains, and you see kinetics in selected grains, very heterogeneous, and also we determine parameters average over the entire sample, like evolution of volume fraction of high pressure phase, each martensitic variance, pressure, shear stress, And we are currently working on developing theory for kinetics at microscale based on these results. But right now in our finite element simulations, we still use our old theory, which still takes into account all what we learn at the nanoscale. And in particular, the effect generates both compressive and tensile stresses. That is why they promote both direct phase transition and reverse phase transition. We have two terms. Nucleation is barrierless. Time is not parameter. That is why accumulated plastic strain plays role of time-like parameters. And also, plastic strain localizes in Wiki phase. That is why we develop very simple portioning rule for plastic strain, and that is why we have a term with ratio of yield strengths in our kinetics. And this kinetics explain well, various experimental results allowed us to predict many results, but today I will focus on first experimental confirmation. This is for alpha to omega phase transition is zirconium for strongly predeformed zirconium. What does it mean? That we produce rolling until hardness saturates and does not change it further, rolling, and this is very important. So we have only one term because we don't have reverse phase transition, and this is our kinetic equation. It's here as a line. This is three different loading pressure plastic strain loading programs, and you see that all experimental points are very close to our analytical expression. So first it's conformation, and second we determine material constant from this conformation. And you see, because it's different pressure plastic strain path, our kinetics is independent of this path. And also we varied initial plastic strain before phase transition, and also kinetics is independent of initial strain. And this is the schematic presentation of this equation. Time can be excluded, but if we keep it, we see that rate of transformation is proportional to rate of plastic deformation. So it can be significantly, drastically accelerated with strain rate, and I will show example for this. Now, this is pressure distributions at various stages, but what is important, this is minimum pressure for initiation of phase transition for different loadings. And you see that it's independent of radius. But plastic strain significantly grows with radius, and path changes drastically. At symmetry axis, we don't have shears, and shears grow along the radius. So that means that minimum pressure for phase transformation is independent of plastic strain and plastic strain path. And immediate consequence is that strain-induced phase transition under compression in the traditional diamond anvil cell and shear and rotational diamond anvil cell don't differ fundamentally. And this was very timely result during COVID, because during COVID we were not able to use to come to synchrotron radiation facilities with our device, but we were able to send traditional diamond anvil cell with sample and control process remotely. And we obtain actually a lot of results, practically the same in the traditional cell as in rotational, but rotational diamond cell still has a significant advantage that it allows to independently control pressure and plastic strain. And this is very important, especially from technological point of view. Now, coming back, actually, the main general problem in studying plasticity, microstructure evolution, and phase transformations is that they depend not only on 5 components of plastic strain and pressure, but also on the entire path. And this, of course, leaves little hope to find some general laws. And actually, this is first law which is obtained for severe plastic deformations and phase transformation. But we have more. we found that after severe plastic straining, dislocation density, crystallite size, and pressure-dependent yield strength also are getting independent of plastic strain and plastic strain path. And for example, to prove this for pressure-dependent yield strength, we develop diamond cell with rough diamond. So we increase height of asperities for diamond cooled from 10 nanometers to several hundred nanometers and produce maximum possible shear stress equal to yield strength and shear. And that is why it was easy to robustly determine pressure dependence of yield strength. And you see it's independent of plastic strain path, and it's isotropic. And still with this relationship, we are able to describe all our pressure distributions. And at each point, we have different plastic strain tensor and plastic strain path, which proves independence. And even more, during phase transition, we found that dislocation density and crystallite size depend solely on volume fraction of high pressure phase and are independent of plastic strain path, and even pressure. And these curves have very important practical consequence. For example, look here, even at 14 GPa and large plastic deformation to reach 14 GPa, we cannot get crystallite size below 40 nanometers. But during phase transitions, we have 5, 10, 20. So actually, and pressure was below 2-3 GPa. So actually, phase transformation is, in this case at least, more effective way to refine microstructures and plastic deformation. And this curve allows us to choose. So first here we have much stronger omega phase because lower grain size. And we can choose based on this curve optimal combination of strength and ductility because alpha phase is ductile and weak and omega phase is brittle but stronger. And also what is important that rough diamond and smooth diamond produce different steady states. And for rough diamond, dislocation density is higher, grain size is smaller, and that is why we were able to reduce phase transition pressure by factor of 2. And this also has important consequence. So that rough diamond change character of plastic flow and something in phase transition. We don't know what, but it produces significant changes. And how to rationalize this? So we know in plasticity that yield surface depends on plastic strain tensor and entire path. And due to this, aqueous for polycrystal aqueous strain-induced anisotropy. But to rationalize our result, we introduce another surface. It's fixed. It does not evolve with plastic strain. And that is why for initial isotropic crystal, it's isotropic. So it corresponds to perfect plastic behavior. And what happened? During loading, stress vector and the yield surface reach this surface of perfect plasticity and then move along it. And that is why material behaves like perfectly plastic, isotropic, and independent of plastic strain and plastic strain path. This is more or less clear for us. But because we have several different steady states with different grain size and dislocation density, we have several such surfaces. And now a key problem for which classes of, of plastic strain path and pressure material behaves along each fixed surface and for which it jumps from one to another. And if we I don't know answer, but if you will have answer, then we will be able to explain why in different technologies like high pressure torsion, ball milling, different extrusions, there is different steady grain size and what we need to change to reach smallest grain size and highest dislocation density. Okay, now next topic, scale effect. So in this paper, I made many predictions, and most of them were confirmed. But one of them actually was opposite to what we observed in experiments. And well, it's not shame to be full, but shame to remain full. So we need to resolve this, right? And what was problem? So stress concentrator at tip of dislocation pileup is proportional to applied shear stress and length of dislocation pileup. Classical length of dislocation pileup is portion fraction of grain size. That is why the larger grain size, the larger stress concentrator, the smaller phase transition pressure, which is opposite to what we observe for zirconium. Where is the problem? Um, well, with all our simulations with three different methods, we found that at large shear stresses, actually dislocation pileup mostly localizes at obstacle, at grain boundary, producing super dislocations. And it's much smaller than grain size, so this is not limitation. But then we need to apply equation for super dislocation, and which stress concentrator is proportional to number of dislocation. And number of dislocation is proportional to shear stress, which can equilibrate this pileup. And shear stress, according to whole patch effect, is in inverse proportion to square root of grain size. So finally, stress concentrator is the smaller grain size, the larger stress concentrator, and the smaller phase transition pressure. This is one prediction, and it's confirmed for zirconium. And second, if grain size is getting too small, then we are in the region of inverse whole patch effect, and shear stress reduces. And also because grain boundary sliding competes with dislocation activity, number of dislocation reduces. So then stress concentrator reduces, and phase transition pressure increases. And we confirm this for phase transition in silicon. Here it's various, it's seven phases, so I will navigate you. You see, this is non-hydrostatic compression, micron particles, silicon 1 to silicon 2, 2.5 GPa, 100 nanometers, much lower, but 30 nanometers is higher. So this is confirmation what I discussed. This is for direct whole patch effect. This is for inverse whole patch effect. And this is very unexpected in comparison with hydrostatic conditions, because here you see with reduction of grain size, phase transition pressure for silicon 1 to silicon 2 increases, and increases again because silicon 2 does not appear, so it's infinity, right? And for silicon 11, it increases and then decreases. So exactly opposite to what we have under plastic compression. And this confirms that we are talking about completely different types of phase transition in comparison with hydrostatic pressure. And some other results. You see silicon 1 to silicon 2 under hydrostatic condition, 16 GPa, under compression, 0.4, and under torsion is also 0.4 GPa. So it's 40 times reduction, and it's the same for plastic compression. Not good. No, computer is okay. It's no, it looks like semi-alive. So it blinks, but does not show. Maybe bulb is dead. Not only projector, don't worry. Yeah. Okay. It's probably programmed for 30 minutes. I need to do this again. Okay. Uh, Okay, then there are some other important results in addition to 40 times reduction in phase transition pressure. For example, silicon 3 does not appear under hydrostatic pressure at all. We obtained it at 0.6 GPa. Then nobody could retain silicon 2. It just disappears under unloading, despite the fact that our first principle simulation shows that it's metastable. We obtain it because we can produce phase transition at low pressure and can manipulate paths. We obtain silicon 2 here in mixture and even poor silicon 2 at some points, and also a torsion. After you see 0 means unloading, we received silicon 2. Then silicon 1. Nobody could receive reverse phase transitions from silicon 2 to silicon 1. It transforms to different phases. Again, we were able to manipulate paths and obtain it. Now, even under hydrostatic condition, look which phases we have. 1, 2, 11, 5, but during unloading, 12 and 3, so completely different phases. That is why post-mortem study of these phases gives us nothing about what happens under pressure. That is why in situ study is very important. And actually, this is a great system because of various phases and complex phase transformation to develop scientific foundation of strain and defect-induced phase transformations for desired nanograin phases and multi-phase nanostructures by manipulating transformation paths, retrieving desired phases, and some possible applications. For example, high-pressure torsions. Torsion is used at 24 GPa and 10 turns to produce some nanostructured metastable phases. We obtain them at 4 GPa and less than 1 turn, and we can, I believe, we can reduce pressure significantly. Also, observed very low pressure for phase transformations. Warns that some phase transition in NEMS, MEMS may occur during contact friction, which is probably non-desirable. So this should be checked and taken care of. Also, our results can be used for quantitative modeling and optimization of different surface processing and for semiconductors, and also for developing regimes of ductile machining by utilizing as plasticity mechanism, phase transition to ductile silicon 2 and amorphous phases. Currently, typical parameters for phase transition in this modeling is 10 GPa, and our results show that they may occur even at sub-gigapascal. So it's qualitative difference. Okay, well, this is our microscale kinetic equation. It's part of our macroscale theory. which we used for solving hundreds of problems for behavior of sample and anvils, reproducing various experimental results. I have time only to discuss this example with solution of inverse problem. So we need to understand something in this field. We need to know fields of stress tensor and plastic strain tensor. They are not measurable. So that is why we developed coupled experimental computational methods. And to prove concept, we took the most complex case, tungsten at 400 GPa. This is experiment from this paper. And we use two lower pressure distribution to calibrate our model, including friction, yield strength, and then two upper higher pressure distributions and four sample thickness profile to verify our results. And you see very good verification, despite the fact that we did not use any of geometric parameters for calibration. And with such good verification, we are confident that our pressure dependence of yield strength is much more robust than known literature data, and we determined for the first time pressure dependence of friction coefficient, and also refined third and fourth elastic constants for diamond and tungsten. And with this verified model, we can calculate with finite elements stress tensor field, plastic strain field, and other fields. Example, graphite to diamond. Under hydrostatic condition, it appears at 70 GPa. Our phase field simulations predicted that it can occur even close to zero. And this motivated low pressure experiments, and indeed diamond was obtained at 0.7 GPa, which is 100 times smaller than under hydrostatic conditions. This is absolute record in pressure reduction. Now, it may, if it can be scaled up, it will have technological consequence. Also, we receive in the same experiment hexagonal diamond at 0.4 GPa, or new orthorhombic diamond. So there is much more from this experiment, but also these results have geological implications. So in geology, in Earth, diamond appears in high pressure, high temperature region. But also microdiamonds were found in low pressure temperature region in Earth's crust. And main hypothesis is that rock from this region subducted to high pressure temperature region, and after diamond appearance, uplifted back. But since we obtained that diamond at low pressure and temperature, but at large plastic shear, they can appear directly in low pressure temperature region in various tectonic events leading to significant shearing. And indeed, these microdiamonds were found in severely sheared zones. And last example, new mechanism of deep focus earthquake. So deep focus earthquake occurs at such depths where pressure is 1223 GPa, temperature is around 2000 Kelvin, and they are generally assumed to be caused by shear bending in due to phase transition in subducted metastable olivine to spinel. But there are many puzzles, and two of them, what are the mechanisms from jump in strain rate from geological to seismic? This is 18 orders of magnitude. And also, how does metastable olivine, which does not transform over a million years in this region, suddenly transforms in the same region within seconds? And we developed several new concepts to explain this. And one of them is natural for us that we treat transformation olivine to transformation in olivine like plastic strain-induced phase transition instead of pressure-induced. And this was not done for any phase transition in geology. And then indeed, kinetics of, we discussed that kinetic is completely different for plastic strain-induced. And strain rate deformation rate, transformation rate is proportional to strain rate. And if we reach high strain rate, then we can indeed increase transformation rate by 16 orders of magnitude. So how to increase strain rate? We found analytical 3D solution for transformation-induced plasticity, or TRIP, in a shear band. And one of result is TRIP shear, which depends on such combination of shear stress over yield strength and shear. But in shear band, shear stress is equal to yield strength and shear. We have 0 in denominator and infinite shear strain. And this explains huge shear strain observed in nature and corresponding strain rate and even more. So what happens here? Plastic phase transition induces trip shear. Trip shear, again, induces strain-induced phase transition. Again, trip, strain-induced phase transition. So we have self-blown up phase transition trip heating process. And when we combine all equations, we found again analytical solution. It still contains this infinity. We were able to quantitatively describe, resolve these puzzles. Quantitatively, I mean to order of magnitude. And we just received conceptual proof that olivine transforms to gamma spinel in rotational diamond cell at room temperature, which never happened under hydrostatic and non-hydrostatic conditions. And rate of transformation is determined to rate of shear, rate of rotation of angles. So depending on rate, we obtain this. This was just 2 experiments. So we obtain this within minute, but if we increase rotation rate by 2 orders of magnitude, we can do this now. It will be within seconds. So this is conceptual proof, and I place my conclusions, and thank you for your attention.
Very nice talk, Valery.
Thank you.
Something I didn't get actually. Do you see the grain size effect, let's say, if you in your plastic here and use phase transformation? Is that if you start with a single crystal, you obtain the same results that if you
No, not at all. Not at all. So if we need grain boundaries to produce dislocation pileup. In single crystal, we don't have it, right? So this effect will be absent. But during plastic deformation, single crystal quite quickly transforms to polycrystal. And then grain size reduces. And the smaller grain size, the smaller phase transition pressure. But then we reach steady state, and after reaching in grain size and in dislocation density. And after this, transformation pressure does not reduce anymore. Yeah, so very strong effect of grain size. Yeah, Arun. Yes, I did not talk about this. If you don't have gasket, during shear, pressure can grow if high pressure phase is stronger. This is so-called pressure self-multiplication effect. If it's weaker, it can slightly reduce. But one of our goals was to get constant pressure, which does not change during phase transition. And we succeeded to do this. You see, this is in computation. So we optimize gasket, sample, geometry, and material. And you see during rotation, pressure practically does not change, and it's very close to minimum possible pressure. And we got the same in experiment for phase transition from hexagonal to cubic boron nitride. So with some experience and with help of modeling, we can control this, but no, not very simple way. Yeah.
The clarification. So if you engage plastic deformation, right, then your transformations are not reversible, right? If you reduce, if you under unloading, you're not coming back to the same material, so it's not reversible. So basically, my understanding is that by engaging plastic, you just change material. And then I'm thinking, there was 70 GPa, now it's 0.7. You're dealing with another material.
Well, it's the same material, but with different types of defects. That is why it's defect-induced phase transition rather than pressure-induced phase transition. But you're partially right that with plastic strain, we may arrest some phases. We may make phase transition irreversible, but some phase transition are still reversible. So they just unstable at completely unstable at room at ambient conditions. That is why we cannot arrest. But defect may arrest interfaces, and this is why it's important to actually to retrieve high pressure phases and use them in engineering applications. Yeah, Dimitri.
Great presentation, Valery.
Thank you,
Summarize,
Dimitri.
we have done many cases, the influence of size and shape, because you showed one example. Is there another scale that comes out of that, maybe because of gradients or concentrations of stresses, beyond the constitutive behavior? For example, it could be initiation and then propagation of phase transition. In other words, the shape and the size, do they play a role?
Size of what? Size of grain or
Not the specimen.
specimen?
Meso scale.
Well, we don't have opportunity to change significantly size. But point is that we are interested in regimes when when grain size is much smaller than sample size, and then I don't think it matters. I don't think it matters. What would be great is to repeat these results with high pressure torsion, where sample size is several orders of, with metallic anvils, where sample size is 2 orders of magnitude larger. But just comparing qualitative some results, I don't see a big difference. Okay, one more example. We had this example, you see huge pressure gradients, huge. When I wanted to approach this problem, I expected that we will need to use gradient plasticity. We don't need this. That means that there is no actual scale effect. Yeah.
There's a big question. This torsion test, it is important to have clockwise or counterclockwise.
No, you can do clockwise, counterclockwise, and in both directions. Partially this direction. Very small effect.
Or sometimes the discussion concerns the pointing effect. Is clockwise or counterclockwise.
No, here it's, well, this is not elasticity, this is plasticity, and this is, we call this torsion, but first when you compress, this is frontal problem. This is already strongly heterogeneous. So for example, here we don't have torsion. This is just pressure distribution due to friction, heterogeneous pressure distribution. That is why superposition of torsion changes, but it does not matter in which direction.